Bonjour. Merci d'être venu. Welcome. Thank you for coming. So this is week number 8. Where are we going? So I hope to finish or almost finish the electron gas by the end of the week. So we will start by looking at the non-interacting density correlation function, which the density correlation function can be measured by electron energy loss spectroscopy, as we discussed at the beginning of the course. But it will be helpful in the calculations that we will do later. So today we're going to discuss the non-interacting case, which is related to just this diagram. And that gives rise to the famous Lindhard function that I will discuss at zero temperature. And then we want to introduce interactions. So before I will do that, I will do very simple arguments that tell us what we should get just from physical ground. Excuse me. So I will first discuss what is the expansion parameter and Thomas Fermi screening. So this is the famous screening we are interested in. And I'll tell you about reducible versus irreducible charge fluctuations that will be used in our calculations later. And we will finish the week with calculating the self-energy in the Hartree-Fock approximation. We will see it gives nonsensical result. And then we will see that if we include screening, in other words, these collective modes, then things start to make sense. So the collective modes we will study by doing perturbation theory around the non-interacting case. So the propagator will be those of free particles. Obviously, all of this should be self-consistent. But it turns out that for collective modes that are mostly controlled by conservation laws and very general properties, the details of the particle, whether they have a width or not, is not that important. So things work out in the end. Now, one of the objectives today will be to compute this diagram. So what is this? This is frequency as a function of wave number. And we will see there's a region in frequency, the momentum space. There's a region where there are particle hole excitations. In other words, there can be dissipation in this region, and we will find what that is. And then next time we will see there's a collective mode, the plasmon. So there's a collective mode that exists here somewhere, and eventually enters this so-called particle hole continuum, and where it is damped by particle hole excitation. That's called the Landau damping. So we will discuss all of this, and we will see how the F-sum rule is satisfied by all this formalism. So is the plan all right? Okay. So there's some formalism at the beginning, but then you will see things will become more physical here, or easier in this case. So first, let's see what is the density correlation function. Again, it will play an important role in screening because why? Because the Coulomb interaction couples to density. So it's not surprising density correlation functions come in. So if I write delta G 1 plus delta phi of 2 plus 2, interrupt me anytime if you have questions. Huh? This is equal to minus time ordered product of psi dagger 1 plus psi 1 plus psi dagger 2 plus psi 2. Okay, so normally when I computed this functional derivative, I had these operators in the opposite side. So I put them back in this order and I put a minus sign. That's what we should do with time ordered product. And this is the density. There's no 1 plus here. This is the density. And this is the density. And I remind you, the plus just tells us that it has to be to the left. So it means that if I compute minus, now I will extract the spin indices. Sum over sigma prime of delta G of 1 plus sigma delta phi sigma prime 2 plus 2. Okay, now the spin index is outside, and now this is only time and space. This is equal to, oh, I forgot here, there is plus G2 plus G1 plus. Okay. So if I put the minus sign here, what will I get? Here, if I sum over the spins 1 plus, I get the density, right? So this is the time ordered product of the density at position 1 times the density at position space-time position 2. And now I have a minus sign, and this is each of these separately is equal to the density. So that's minus n squared, right? Because this is psi dagger psi at the same place and psi dagger psi at the same place, so it's a density. Which can, and this can be written just as a time ordered product of n1 minus n times n2 minus n. Because the expectation value of n1, that's what I call the density. And so this quantity is exactly what we called before, what we called the density correlation function, 1 minus 2.
Small question.
Yes,
we said that J2 2 plus is the density, and J1 1 plus is also the density, but shouldn't they be the density at point 2 and point A?
Yes. But now I should have mentioned, there's no phi anymore here, so we are recovering space. I mean, time translation invariance in space.
Oh, okay.
Okay. And there's no time dependence as well. I mean, if I just look at the density at the one point, I mean, there are fluctuations, but the average is well defined. It's not time dependent. Okay. So now I look at this, and you see that this is equal to minus sum over sigma of G 1 minus 2 sigma times G of 2 minus 1 sigma. Okay. So why? Because I have 1 and 2, so 1 and 2, and this is also 2, so I have 2, and this is 1, so I have 1. Okay. Now, why do I have the same spin? I lost one of the spin sums, right? And the reason is just because these 2 points are at the same location, and the spin, so here and here, they have the same spin, and spin is conserved. So the spin at the end of this line has to be the same as the spin at the beginning. Same for this. So there's just one spin that survives. Okay. So the plan is that we will just take the Fourier transform of this, and this will be the Lindhard function. So any question with this? Okay.
Why is there suddenly a minus sign?
Because of this minus sign. Okay. This was delta G, delta phi was equal to GG. Now I put a minus sign there. So there's a minus sign there.
Okay.
Okay, good question. I mean, it's hard to follow these minus signs. Sometimes I forget to specify. Okay, so if we take the Fourier transform of this and the Matsubara transform as well, so we get chi nn of q and IQN is equal to, okay, here I will use the convolution theorem. Okay, so there's a minus sign, and the sum over spin just gives a factor of 2 because this is independent. Then there's the temperature times the sum over Matsubara frequency, IKN, times the integral d cube k over 2 pi cube, times the G times the G of the k IKN, G of k plus q times the IKN plus IQN. Okay. I will drop these arrows very soon. Okay. So this is just the convolution theorem. So here I have 1 minus 2, 2 minus 1. I take the Fourier transform. So the Fourier transform, you see in real space, it's just the product of the quantities, but with 2, 1. But in momentum space, then it's this convolution. Okay. If you're not convinced, and you have the right to be not convinced, you can just try to do it at length. Okay. But this is just the so one way to see this is that we are coming with the momentum q here, going out with another momentum q, and here we have k plus q, and here we have k. So at each vertex, the momentum is conserved, and this is really what we have. Okay. So now if I write the explicit form okay, in Feynman, by the way, in the Feynman way of doing things, there's one loop. So that's why there's the minus sign. But here, it's not the way it comes out. We just use this. Okay. So now if I write this explicitly, I have, okay, the objective now is to compute this. This is the Lindhard function. So that's for the non-interacting case, and it's equal to minus 2 t sum over IKN of integral d cube k over 2 pi cube. Now I know this, okay, this is 1 over IKN minus zeta k, where zeta k is epsilon k minus mu. That's the non-interacting case. And this one here is 1 over ikn plus iqn minus zeta k plus q. Okay, do you have any questions? Okay, so we will do the sum over Matsubara frequency. So one way is to do this this integral in the complex plane, and to go through. Now there will be two poles when we fold back to the real axis, and that's one way to do it. We will use another way, which is easier when there are not too many poles, but when there are many poles, it's better to use the other method I was mentioning. But okay, here when there are not many poles, the way to do this is like this. It's a 2t sum over ikn integral d cube k over 2 pi cube. And then we use partial fraction. In other words, we write this as 1 over ikn minus zeta k minus 1 over ikn plus iqn minus zeta k plus q. And then when I put back in the same denominator here, I will have 1 over iqn plus zeta k minus zeta k plus q. Okay, you see this? If I put on the same denominator, then this goes there, the ikn drops, and I'm left with iqn minus zeta k plus q plus zeta k, because this goes there with the minus sign. Now I know how to do these sums. But we know that these usually need a convergence factor. But in reality, we have a sum that goes like 1 over ikn squared at infinity, so it converges. So whatever convergence factor we put here, if we put the convergence factor for tau equals 0 plus or tau equals 0 minus. So in one case, it will give the Fermi function minus the Fermi function. In the other case, it will give me the Fermi function minus 1 minus the Fermi function minus 1. The minus 1 drops out. So whatever I do, I get the same answer. And this answer, then I can do t times sum over ikn, I can do. So this is now equal to minus 2 times the integral d cube k over 2 pi cube times the Fermi function of zeta k minus the Fermi function of zeta k plus q divided by iqn plus zeta k minus zeta k plus q. Now you notice that here I have used the fact that this is a bosonic frequency. So bosonic plus fermionic is a fermionic frequency. So the sum over ikn here has just given a Fermi function. The iqn doesn't matter. Okay, it's fixed. The iqn is here. So it just shifts the sum over these Matsubara frequency. But anyway, they go from minus infinity to infinity. Okay. So now suppose that I want chi retarded. Okay. So I want chi retarded of q and omega. What do I do? I just replace this by omega plus ieta. Okay, very easy now. You see? So I have the retarded response, and that's what's called that's what's called the Lindhard function. So you see, we have used all our tricks now. We know we know how to sum over these fermionic frequencies, and we know how to do analytic continuation. So we have a clear example of all the tricks that we have used, or all the technology we have developed up to now. And you see, one important thing is that I need to do the sum over Matsubara frequency over IKN before I do the analytic continuation. You see, if I had done the analytic continuation here, then I would not have known what to do there. So you cannot reverse these orders. It's only when all the Matsubara frequencies have disappeared out of sight and you're left just with the external frequency here, IQN, that you're allowed to do the analytic continuation. Because that's the way we derived this, right? We wrote that KNN, the Q IQN was some integral of some chi double prime, and then there was IQN plus, but the chi double prime did not involve any Matsubara frequency. It was just all in real frequencies. So that's an important thing to remember. You have any questions?
Where did the T disappear?
The T goes with the sum. It's T times the sum. It was 1 over beta times the sum that gave it Fermi function.
Oh, yeah, right. Right.
Yeah. Good point. Okay. So now I'm going to do two things. One is I'm going to rewrite this in such a way that at 0 temperature, you can compute this function just by doing some integrals. I will not do all the integrals at the end, but I will just set it up in such a way that you see that it's easy. It's some integrals to do. Okay. And then what I will do is I will look at the imaginary part of this. In other words, I look at where there is dissipation, and I will work out these limits here and show you where this is. But first, I write it in such a way that you can do it, that you can do the integrals. But before I do that, notice that here I call that the particle hole excitation, right? And you see why. If zeta k, take a 0 temperature, if zeta k and zeta k plus q are on the same side of the Fermi surface, okay, both of these are 1, so you get 0. Or both of these are 0, you get 0. So you need one that is outside the Fermi surface and one that's inside the Fermi surface. So one is a particle, the other one is a hole. And you remember that the imaginary part, chi double prime of NN, I forgot the NN. Chi double prime NN of Q and omega was odd in frequency. So this, if you take chi double prime, so the imaginary part of this, you can check that it is odd in frequency. Basically, it will exchange these quantities, and that will be odd in frequency. So I will compute only the imaginary part, and the real part can be obtained by Kramer screening. So the imaginary part now of this, so chi double prime and of Q and omega is equal to, so I use the Weierstrass-Sokatsky formula, right? I write this as minus I pi times the delta function. So that gets rid of the minus there. And pi times 2 is 2 pi, so I get 2 pi integral d cube k over 2 pi cube of f of zeta k minus f of zeta k plus q times delta of omega plus zeta k minus omega plus zeta k minus zeta k plus q. Okay. Now, one thing I can point out already here is that you see that, so we have absorption here, we have some non-zero kite prime when the omega, the energy here, coming here, is conserved, right? In the sense that this energy is equal to psi k minus psi k plus q. So in other words, if the imaginary part I can find by cutting this diagram in two, if you want, somewhere. And here, if energy is conserved, in other words, the energy omega that's coming in is equal to the zeta k minus zeta k plus q. They go in opposite direction. In one case, you take away from the Fermi surface. In other words, you add outside. Then you get a contribution. And the other processes where energy is not conserved in the intermediate states are virtual states, right? They contribute to the real part. Okay, so so we can write this as 2 pi, and we can go to spherical coordinates. So if you go to spherical coordinates, there's a phi. We can integrate over phi. That gives another 2 pi. Because you see nothing. Here you have in psi of k plus q. So you have the cosine here, okay, between these two angles, between these two vectors. But you don't have any azimuthal angle. So this is why I get the 2 pi square. And this q square over 2m, this is what I call the epsilon q here. Okay. And so you see that when I take this difference here, I will be left with, okay, integral from 0 to, from 0 to k for me. You will see why. I mean, I'm going a little bit ahead of myself here, but I go, okay, spherical coordinates. So I get k squared dk, and I get integral from -1 to 1 of d cosine theta. And this, just by changing integration variables here, I can change integration variables from k to k minus q. Then this will be the same f of k as here. Okay, so in this term, I change k for k minus q. Okay, that's the idea. So here I have just one f of q that is common to this delta. Well, there will be two delta functions. The delta function will become different, but there's a single Fermi function of zeta k, which means that the integral here goes from 0 to k Fermi. And then I have two delta functions. I have delta of this one here. So you see that if I take k squared over 2m minus this, well, the chemical potentials drop out, and the k squared over 2m drops out. So I'm left with minus this, minus kq cosine theta divided by m plus epsilon q, and minus minus delta of omega. Now, if I change k by k minus q, this becomes k minus q, and that becomes k. So I will have omega plus kq cosine theta over m. And the here, the epsilon q, there was a minus here because it goes with this, and there's minus. So there was minus, and here there is plus epsilon q. Okay. So you see that it's doable. I mean, it's not a problem here. One thing you can do is use the property of the delta function here to rewrite this term here as m over kq times delta of omega minus epsilon q over kq over m minus cosine theta minus delta of omega plus epsilon q over kq over m plus cosine theta. Okay, so the integral over cosine theta is easy to do. You see, you can use just the delta function. But you have to be careful because this quantity needs to be contained between -1 and 1. This is why we get all these bounds there. Okay, and then the integral over k, well, I mean, it's just get integral over k. Okay. In the notes, I quote the result for d dimension. You can do that in 4 or 5, any dimension you want. And then you have prefactors that are given by gamma functions and so on. It's cubed, okay? But we won't waste too much time doing this. I just want to show you how to do it in principle. What I want to do instead is work on these bounds here. Why we have this, sort of develop a physical intuition for this. Is it okay? You have any questions? Okay. So we will start from this this expression, okay? And so here, if we work with the chi double prime, plus 2 pi, then I get this difference, and I get delta delta of omega plus zeta k minus zeta k plus q. Okay, and because this is an odd function of frequency, we just need to worry about one case. Let's see the case where omega is positive. Okay, so we take omega larger than 0, and we will take psi of k plus q larger than 0, and psi of k less than 0. Okay, because we want a 0 temperature and we don't want these to be on the same side of the Fermi surface. So I need to have opposite signs here. And then I will have omega equals psi of k plus q minus psi of k. So omega will be positive if I do this hypothesis. Okay, so let's start with this line here. So if I take, let me have the filled, the empty Fermi surface in red. And the filled Fermi surface in blue. Okay. And I have Q is the distance here. And this is the case Q larger than 2K Fermi. Okay. Because K Fermi, K Fermi. So here I have some vector, let's say K. And this vector is K plus Q. Okay. So there is a minimal frequency here, which is what is the minimal frequency that we can have. The minimal frequency corresponds to this case. Kf and here where I have so Kf is in the negative direction corresponding instead of Q here, and here I have Kf plus Q. I did everything backwards here. Okay, I did everything backwards. This is the field. Sorry. And this is empty, right? Empty in the sense that the K plus Q is outside the Fermi surface. Okay, so you can think of this as field, but the K plus Q is outside the Fermi surface, outside that Fermi surface. And this one is inside. So I have that omega min will be equal to zeta of yeah. Okay. Q is this vector. So the length of this vector is minus Kf plus Q. Okay, this is shorter than the original vector. So I have zeta of minus Kf plus Q, and I have minus zeta of Kf. So what is this? So Kf squared will drop out, and I'm left here with minus Kfq over m plus epsilon q. Okay, plus q squared over 2m. So that's this boundary here. Okay, I have minus, no, kf over m is V Fermi. So I have epsilon q minus V Fermi q. Okay, and then there is the other side. There is the largest frequency is when the largest frequency is here. Largest frequency is when I have this here, and this guy all the way here as well, right? I have so now this the vector here kf plus q goes all the way here, so it's plus kf plus q, right? So when I do this, then I have plus here and plus there, and it is this boundary here. So you have to imagine that this continuum and there's a minimal frequency and a maximal frequency. It's not very well drawn. I mean, it goes like that. So if you go up like that, you hit this also. Okay.
Why or okay, we have the vector q and k. Why are we always starting from the center of the empty region?
Okay, it's because I defined psi k to be in the field Fermi surface. So f here. So I multiply. I have f here.
No, not this vector. The other one.
The other one here.
Yeah.
So here again, I'm looking at the k plus q. Okay, so I have q here and k there. So k plus q is this vector.
Okay, so q is just a parameter that we chose.
Q, yes, q is the external parameter. Yeah, it's the external.
Yeah. But why would it? Once we chose the parameter, why would it put it in the center of the empty Fermi region?
Because it's always multiplied here. It's always measured with respect to the Fermi sphere here. Okay. So we have a Fermi sphere here, f of k, and we have another Fermi sphere here, which is shifted by q with respect to this one.
Okay, yeah.
Okay.
Yeah.
So now we just have to look at the other case, which is the q less than 2kf. So if q is less than 2kf, then the spheres overlap, right? We have to think of this as spheres and they overlap. So I have to redraw everything. Well, even if they overlap, you see that the omega max will be the same as the one I just did there, right? I mean, the spheres overlap, but it will be the same. I mean, so here I'm looking at the q less than 2kf. So I'm looking at this region. And I hit this curve as well. I mean, the last one I did, this one here. So this one is still there. What I need to explain is just this little red region here, which is the omega min, right? So we do q less than 2kf. So we will have this one here. And this one. So now I have q do here. And what is the minimum value? Well, it can it's possible to have both k let me write this. It's possible to have both. Well, okay. Let me first work something else. Okay. So you see that if I have a k here and k plus q here, then this delta function here, and that was the case before also, I just didn't say it. To keep this, I mean, I want to satisfy omega. So k plus q minus k, so I need to satisfy k, q cosine theta over m minus q squared over 2m. But what is this in terms of geometry? You see that this is just like vector k dotted into another vector q equals a constant. And if you remember, that's the equation for a plane. If I can vary k here. So in other words, if k dot q, so kq cos theta is equal to a constant, it means that I have a length here that is constant, that is k cosine theta. And I have a plane here. I don't know how to draw a plane, but something like this. And this arrow here is in that plane. And that point here is in that plane. Okay. So to satisfy this conservation law here, I can be anywhere. I have to integrate k anywhere in that plane. Now you see what will happen if I get to this point here. When I get to this point, I want to be outside this Fermi surface and inside that one. So what will happen? Well, what will happen is that I will have, instead of integrating over, I have to look at the intersection of this plane with the sphere. So that is sort of a filled circle here. But when I come here, what I will have is an annulus. Okay, again, I don't know how to draw this, but you see what I mean? I come here with this plane. I have to integrate. The plane here intersect the sphere, so it's like a circle, a filled circle. But when I come here, I have to be outside this blue sphere. So the only thing that counts is this ring. Okay, you have to, if I look at this like this, I see a ring. Is that okay? So that's why there is this red region here. This point here, this line, I'm sorry, corresponds to the point where as I move here, I hit the point where I have to go from a filled circle to an annulus, to a ring. So where is that point? Well, that point is when, well, what is that? Where is that line? that line is when I have the vector k here goes to that surface here. So this goes to, this is the, it starts from the center here, and it goes to that surface. And now starting from the center, I have that this length here is equal to Q, okay? And I know that this length here is equal to K Fermi, okay? It's at the Fermi surface. So I have K Fermi. So it means that Q here is equal to K Fermi minus K, okay, because K is in this the reverse direction here. Okay, so now when I compute this these guys here, I have to compute. Yes, it's so running out of space. So I have to compute zeta of k plus q minus zeta k. So zeta of k plus q is, okay, k plus q is kf. So that's zeta of kf minus zeta of k. So k is kf minus q. So what is this? So that is VFQ minus minus. Okay, so here the cross term is V Fermi times Q with a minus sign, and minus sign there's plus, and there's epsilon Q squared. So it's VFQ minus epsilon Q. And it's a real miracle, but apparently I have the same answer. Okay. So that explains these boundaries, and it shows that I didn't have time to do all of this. Okay, but we'll do next time. Okay, so to summarize, we computed the density correlation function. So these 2 points are at the same place. These 2 points are at the same place. So the density correlation function in space-time is just G12 times G21 with a minus sign. We did the Fourier transform, and we did the analytic continuation. And so we discovered that we need to have particle hole excitations. You know, if a particle is outside the Fermi surface, the other one is below, and vice versa. Okay. So as this k here runs over all possible values, sometimes it's this that's above the Fermi surface, sometimes it's this. But the point is that they're always on opposite signs, at least when t equals 0. At finite temperature, they can be on the same side a little bit. And we saw that if energy is conserved here in the middle, then that contributes to the imaginary part. Otherwise, for the real part, we have virtual processes. In other words, this omega is not equal to this. So even though we conserve energy at every vertex, it doesn't mean that, you see, it's different from asking that it's the frequencies that are equal, that are conserved, the frequencies that are conserved. But it's not the same as saying that the frequency is equal to the energy difference measured with psi k plus q. So next time we will see that there's We will see it very simply first, and then we will see that there's a plasmon here that hits this particle hole continuum eventually. So that will be, in other words, we will treat this in the random phase approximation. Okay, are there any questions? Okay, sorry that was so slow, but this is really confusing. So I don't, apparently I've not done such a big mistake. Okay.
All right, thank you.
So I will end the recording and stay around if you have questions. Otherwise, I see you on Wednesday.
Thank you very much.
See you.
Okay, thank you.